Hello everyone, we have been discussing the transient flows through unsaturated soils, extent where we can solve the exact formulation. We have an exact formulation for the transient flows. So, using the Boltzmann transformation, we can solve the theta form of Richard's partial differential equation, and we get an ordinary differential equation. Then when we integrate it, we get the equation for d of theta, diffusivity. Here the diffusivity is equals to minus half times d lambda by d theta at theta x. Earlier I would have written theta I, that is at given point, into integral theta initial value, that could be 0 or something, theta naught maybe, to theta x, that is at any given point, and lambda of x dx. If we solve this, here x is a integration variable. So, if we solve this, we get d theta, d variation, diffusivity variation with theta. D is the hydraulic diffusivity, which has units of meter square per second, we discussed earlier. How to solve this particular equation is the question. Now, we need to conduct an experiment for obtaining theta of x and t. So, this can be done by compacting a soil sample into a column. And connecting this column, this may be porous plate or something, and then which is connected to a reservoir. So, if you maintain a constant head of water and you take sufficiently long column so that an infinite boundary condition can be invoked. So, then this is a particular head that is maintained, positive head that is maintained, that is H naught. This is the initial condition, and in terms of theta, the initial condition is at this particular point, that is at x equal to 0 at any given time. This is equals to theta s, volumetric water current. Here within the soil sample, the initial condition is that at any given x greater than 0, when time t equal to 0, this is equal to initial value, or you can write as theta naught or whatever. This is the initial condition. And this is one boundary condition, inlet boundary condition, and other boundary condition, that is at theta at x equal to infinity. At any given time, this is invariant. That means d theta by is equal to 0, or with respect to x is 0. So, there is no flux here. So, with respect to x, this is 0. This is the boundary condition we invoked, or simply this is theta at x equal to infinity at any given time. This is simply 0. This is simply is equals to theta initial. So, this is a constant value, therefore, if you differentiate it becomes 0, it is 0 anyways. Now, such an experiment can be conducted where you have a long column, so that this boundary condition is satisfied and always a constant head is maintained. Then you can maintain, then the theta is also becomes theta equal to theta s. Then after a certain time, we can measure the water content at different points within the soil sample, either by placing sensors at different locations or by destructive technique. We can establish theta at any given x at one particular time interval. This can be estimated. So, the theta variation with respect to x at any given particular time t1 can be estimated from the measurements. So, this is the measured data. So, knowing spatial location, so this how does it vary? So, this varies in this particular manner. So, the gravimetric water content or theta volumetric water content, if you plot with respect to x, so then it varies in this particular manner. So, this is equal to theta initial or theta naught, and this is theta s. So, beyond this point the water has not reached. So, wetting front is somewhere here, but there is a water distribution within this entire space from theta s to theta initial value. So, the sharp wetting front cannot be seen, that is only hypothetical, and mostly that can be invoked in coarse grained soils without much loss of accuracy. So, this is volumetric water content versus x, this is the observation you get. So, this is at one particular time t equal to t1, that is observation. As we know the how theta varies with x and t, we can obtain lambda, which is x by square root of t. So, we can also plot how theta varies with lambda, because this variation is also similar. So, even though the x axis scaling would be different, so this will be similar, because it is simply x by square root of t. T remains constant, because at one particular time interval for different x values you are obtaining, it will be scaled and you will get the same qualitatively similar data. So, this is the data we require for this particular analysis. I will draw this one here. So, this is lambda, Boltzmann variable, and this is theta. So, now this is theta, and so this varies in this particular manner. So, this is the observation, this is theta initial value. Now, this integration means at any given point, that is theta x, at any given point x by square root of t. So, this area is simply integral theta initial, that is this point, to theta x and lambda of x dx. So, this can be simply obtained by numerical integration. You can take discrete points, because data will be available. So, we can take discrete points and we can calculate the area under this particular curve. This hatched portion can be obtained for any given data, and if this is obtained and at this particular point the slope can be obtained, that is d lambda by d theta. So, this in fact is slope is minus d theta by d lambda at theta x, and that is what you are getting here, because the slope of this one is d theta by d lambda. So, if you inverse it, this value can be substituted into this, and this portion area is coming directly can be substituted here. So, essentially by multiplying with minus half and the slope of this point at this on the curve at this particular point theta x, and integration, that is the area of the hatched portion, should give you d theta at x at this particular point. Similarly, discrete data of d at different theta x values can be obtained. So, if we plot that, so that appears to be, so on y axis you can plot d theta or simply d, and x axis you can plot theta, and theta varies from theta initial to theta s. As theta increases, the d theta value increases like this. Maybe several orders of magnitude changes from here to here when theta changes over a small value, like say initial value of theta maybe could be 0.1 or something, and or 0.01, and theta s could be say 0.4 or something. So then it can change in this particular manner. So this is how the hydraulic diffusivity can be obtained. Using graphical technique, it can be easily obtained. So this is a very popular technique in soil science, and this particular equation is called Bruce and Clute equation because of their contribution in the derivation of this particular expression, and graphical solution is also commonly used for obtaining the diffusivity. So the diffusivity helps in understanding how fast the water diffuses in the soil. Often we may require to solve the original partial differential equation of either mixed form or theta form or head form, depending on the situation, and the Richards equation, that is that equation is theta form is dou theta by dou t is equals to dou by dou x of d dou theta by dou x. So this is the theta form of Richards equation, and we earlier simplified this to dou square theta by dou x square times d, assuming that the d variation with respect to x is negligible. So this we applied in case of a small sample which is tested in axis translation technique or pressure plate operators using the method of multi-step outflow technique for the estimation of hydraulic conductivity function. So in that we made a similar approximation, however the representation was in the head form, or the suction was used as a dependent variable. Here the dependent variable is theta, volumetric water content, and this form, that is dou theta by dou t equals to d times dou square theta by dou x square, exactly replicates the fixed diffusion equation for ion movement within the any media, porous media or any other medium. So this is exactly similar to that. Either this can be approximated like this, or the whole equation need to be solved, or the mixed form need to be solved very often. So that can be achieved by considering numerical approaches. So far we are trying to understand how analytically the problems can be addressed, but for complex problems and complex boundary conditions, it is not possible to obtain analytical solutions. Moreover, in the field we do not expect simplified boundary conditions and one dimensional flows very often. So in that particular case, the numerical solution can be advantageously used to solve these problems and address those field issues. So I'll demonstrate how one particular type of finite difference approximation can be used to solve the partial differential equation, and this is a demonstration purpose only, and extensive understanding on this particular finite difference or computational fluid dynamics requires a specialized training. So here only its demonstration will be done. So I take a simplest form of the expression, that is dou theta by dou t is equal to d dou square theta by dou x square. This is a linear form of partial differential equation and a parabolic partial differential equation. So I will demonstrate how a numerical solution for this particular case can be obtained. Generally in computational fluid dynamics or finite difference technique, we invoke the Taylor series expansion. For example, if you have a function f which is varying with x, if there is a function that exists like this, then at any given point x, I can expand the function around this particular xi. So, this difference would be delta x. So, around this particular region of delta x, I can expand this particular function. So, if I expand that, I get f of x plus delta x. So, therefore, I can invoke the Taylor series expansion, that is for f of x plus delta x, this is equals to f of x plus delta x times f dash of x plus delta x square by 2 factorial f double dash of x plus so on and so forth. Similarly, for f x minus delta x, so that is for this particular point. So, this expression becomes f of x minus delta x f dash of x plus delta x square by 2 factorial f double dash of x minus so on and so forth. Using these expressions, we can obtain first order difference expressions. This differential equation will be expressed in the form of difference equation, so that we can generate algebraic equations to solve these equations and finally solve. So, as we are saying, there is a small increment of delta x considered, and around that we can expand this function f of x in this particular manner. So, therefore, what we could do is the theta variation with x and t we want, and we do not know how it varies. Here there are two independent variables, that is time and spatial variable x. So, now what we assume is that we consider a grid, a domain. So, the theta variation over a column length of say x centimeters. So, this is the domain that is shown. We divide this domain into small cells or grid points. So, now you have say this particular thing is I, this is I plus 1, this is I minus 1. So, starting from 1 etc., 2 etc., up to say n number of points I can consider on this particular domain. So, my intention is to obtain, this is a spatial x and this is temporal. So, how the theta variation happens along the spatial length at any given time, so that is t equals to 0, I want to understand. Here as it does not start from 0, this is 1, this is 2 and this is 3 and so on and so forth. So, here x equal to 0, that is first point, grid point, and x equal to n, that is the last grid point on this domain. Similarly, in the time domain, time t equal to 0, that is nth time step, or n equal to 0, 1 time step. So, that means n equal to 1 time step, this is I equal to 1 time step. So, again we divide this into number of time intervals. So, n equal to 2 etc. So, this is n, this is n plus 1, this is n minus 1, so on and so forth. We are now getting the volumetric water content variation, how it varies in the spatial domain of the problem, how it varies at discrete points we can obtain. Similarly, with time, how it varies at discrete time intervals, what is the value we can obtain. So, essentially we are changing the continuous form into a discrete form. So, that is what is called difference form we are getting from the differential equations. So, this is n equal to 2 and this is n equal to 3 or some other time interval. So, here what we are trying to do is we express the theta to obtain this difference form. Now, we can simplify the dou theta by dou t term, that is a differentiation of this particular equation can be made in difference form by considering dou theta by dou t as the first derivative of theta with respect to time can be obtained by considering this particular equation itself. So, from this particular equation, f dash of x can be written as f of x plus delta x minus f of x divided by delta x plus some higher order terms. So, if I consider a delta x term which is very small, delta x approaches 0, very small delta x, then these higher order terms can be ignored. So, when you ignore, essentially the slope or the derivative of the function can be approximated into a difference form like this. So, now this particular dou theta by dou t, there is a first order differential form, can be expressed as theta x plus delta x I can write, or I can simply write that this is I plus 1th value, because x plus delta x. If I consider at ith point, then this is I plus 1th point minus theta at ith point divided by delta t. So, this is in the time domain. So, now I can solve this particular form in the nth level itself. N could be 1 and I could be 1 in this particular case likewise, or I could be 2 in this particular case, because I equal to 1 becomes a boundary condition. So, I equal to 1 becomes a boundary condition. What happens at the boundaries? We already know the information. Theta at x equal to 0, that is equals to theta s, that information is known. So, this can be approximated to this. Now, you have second order differential equation on the right hand side, dou square theta by dou x square. How to obtain difference form for this particular equation? So, we can use these two equations. When you add these two expressions, what you get is f of x plus delta x plus f of x minus delta x is equal to 2 f of x, these two terms get cancelled, plus, so this is simply delta x square f double dash of x plus some higher order terms. So, now if I write the expression for f double dash of x, this is simply f of x plus delta x plus f of x minus delta x minus 2 f of x divided by delta x square. This is called central difference and this is called forward differencing, etc. But I am not discussing the details of what is central difference, etc., etc. Central difference, higher order terms, there is a second order approximation, or these things need not be discussed here. So, the dou square theta by dou x square term can be approximated as, based on this theta, x plus delta x is I plus 1 minus 2 theta I, f of x is theta I, plus theta x minus delta x is I minus 1 divided by delta x square. So, now if I substitute this one and this one in the differential equation, what we get is theta I plus 1 n minus theta I n divided by delta t is equals to d theta I plus 1 minus 2 theta I plus theta I minus 1 by delta x square. If I simplify, this is an explicit form of finite difference approximation. So, here I can write for theta I plus 1, sorry, this one is not theta I plus 1. So, this is at essentially at same ith level. So, this is at I and n plus 1, only time step is varying, because we are actually doing the difference operator on the time step. So, this is n plus 1. So, here, sorry for the mistake. So, this is n plus 1. So, therefore, this is n plus 1 can be written as theta I n plus d delta t by delta x square times theta I plus 1. These are all at nth level. This is my approximation. I am considering at nth level these values. So, minus 2 theta I n plus theta I minus 1 n. I choose to consider them at nth level. So, now if you closely observe theta I at n plus 1, for example, if n is equals to 1, so at the second interval ith level, this point is calculated using theta I at nth level. So, that is this particular point, and theta I plus 1 at nth level. So, that is this point, and theta I minus 1 at nth level. So, this is this point. So, using these three different points, this point is calculated. So, as we have initial condition in this particular case is theta at any given x greater than 0 when time t equal to 0 is equal to theta initial. So, therefore, we have the knowledge of theta along this grid. So, knowing these three terms, we can obtain theta in the next time step. So, this is a delta t and this is a grid point between two different points is delta x. So, essentially for any small delta time increment, what happens to theta, how theta distributes along the spatial domain can be obtained, spatial distance can be obtained. So, the next time level again, so similarly for this particular point you utilized these 3 points, for this particular point theta I plus 1, theta I plus 2 you utilize these 3 points, known points. Similarly, you can obtain all points on this particular nth level, n equal to 2 level. Then once you obtain all these values, you increase the next time increment, again this point can be obtained by utilizing these 3 known points. Similarly, you march in time from n equal to 1th level to 2th level to 3rd level, etc. You march in time. So, these therefore, these finite difference techniques are called time marching techniques. So, we march in time and step by step we estimate how theta value changes with spatial distance for different time intervals, and now any given theoretical time what is the theta value can be obtained along the spatial length. So, this is simply the explicit finite difference scheme we call. So, one can obtain the stability and convergence of these particular expressions or equations, and based on how this d delta t by delta x square changes, one can obtain the convergence and stability criteria can be developed. How error propagates if you change the delta x or delta t, etc. can be studied, and this is one type of scheme in the finite difference, and there are other schemes like implicit scheme where if you put n plus 1th values here, so then if you put n plus 1th values here, then this becomes implicit scheme. So, because you have n plus 1 on either side of the equations, only nth term, only one particular data point is there, then it needs to be solved by numerically. It will be more rigorous because it is an implicit scheme. So, by Gauss elimination or such kind of techniques we utilize to solve these expressions to theoretically obtain theta of x and time theoretically. So, in inverse problems, essentially you may want to estimate what is the d value knowing theta of x and t experimentally. So, then in particular case we utilize optimization techniques, because earlier I have shown that if you have theta measurements xt and theta theoretical, then the difference between these two data points can be taken and error can be computed, and this error can be minimized by utilizing several optimization techniques. So now I will demonstrate one way of estimating the theta of xt for a known data of hydraulic conductivity function and soil water characteristic curve, because once the diffusivity is known, our knowing actual equation is that this is dou theta by dou t is equals to dou by dou x of k dou h by dou x. So here h of theta, if this function and k function are known, so then you can obtain theta of xt by numerically like what I have shown here. So such a methodology is utilized in one of the freely available software called Hydrus 1D, which is developed by the same authors who developed RETC, which I earlier discussed. So this is Hydrus 1D, and Hydrus 2D and 3D are also available, but they are paid software, they are commercial, and here you can choose one particular name and you can write some description. So then you have this pre-processing window. You can select the main process. In that the water flow, that is what we want to solve through unsaturated soil, and vapor flow we haven't discussed, and you have solute transport and many other options, heat transport and root water uptake and many other options. Here we will concentrate on water flow alone, and this inverse solution is nothing but what I discussed earlier, that if you want to estimate the hydraulic conductivity function and soil water characteristic curves, knowing the volumetric water content distribution with time and space, you can estimate those functions by inverse solution. So the inverse solution means that. Then you select next. So then length units can be selected as in centimeters, meters or millimeter, and number of soil materials. So it can handle layering system or non-homogeneity. So you can select number of layers, and each layer you can give what is the different soil material that is available, and whether the flow is taking place vertically or horizontally, that can be seen here, that can be understood, because here it mentioned that decline from vertical axis, if you put 1, that means it takes vertical flow, and if it is 0, then it simulates horizontal condition. So here I was saying the number of soil materials can be considered for non-homogeneity. So the depth of the soil profile by default is 100 centimeter, and here you can change if you have any other values. Then if you select next, so here the time information, you have units for time, seconds, minutes, hours, days and years. The default value is days, and I keep the days. Initial time is 0 and final time is 100 days. So you may choose maybe seconds or minutes, and then this is initial time and final time, and you can consider time variable boundary conditions also. So for every one time step it gives the output, print options, and print regularly. You can play with these options available. So number of iterations you can select, maybe 100 you can select, or you can give the, so you can select maximum number of iterations to be 100, and these are tolerance, etc. And if I go to next, so here the choice for hydraulic model is given. Here if you consider single porosity model, you have Vanjanish Moolam, this is what we discussed in our one of the lectures, and with air entry value, if you enforce -2 centimeters, then the stability will be satisfied, so it will be smooth, it seems, as it mentioned in the manual. And you have modified Vanjanish, Brooks, Corey and Kosigi models, and you have other dual porosity models also, and you can consider hysteresis if you are considering cyclic effect of drying and wetting. So, if you consider a simple problem, and here theta r residual water content, the QR means theta r, residual water content is 0.078, that is the default value, and theta s is 0.43, this is a porosity or saturated volumetric water content is 0.43, alpha is 0.036 and n is 1.56, and Ks is this value 0.017 centimeter per minute, which is considered. So, these are the values for loam soil, and you can also select different soils from the menu. Here you can select boundary conditions for this particular cases. You have constant pressure head, constant flux and atmospheric boundary condition with surface layer, etc., etc. These are under pressure boundary conditions. So, you can select either pressure boundary conditions, because essentially you have a mixed form to solve, and you can input the boundary conditions in terms of head or water content. So, if you change it to water content boundary conditions, then you have a constant water content at the upper boundary. This is theta s, constant water content is theta s, saturated water content or constant flux, etc. you can go, and lower boundary constant water content, constant flux or free drainage, etc. you can select. So, we give in water contents only constant water content we give. And next, do you want to run profile application? Okay. Save data, yes. So, this is your mesh, and you can consider. So, the initial input so far it is not taken anything. So, this is the initial input, and if you close this, so this is how the grid is considered. Here the theta variation is not considered at all, and here we need to give input. So, here theta is given as, so this is not theta, this is head. So, it is wrongly considered. We go to previous. So, here we go and go for options. So, here we go for pressure head conditions itself, because it is not taking the water contents now at present. So, pressure head consideration if you take, and then if you consider the initial conditions, then this initial condition is selected here. So, then we can proceed, and the initial condition is that at x equal to 0 or z equal to 0, the head is 0, and all other points this is minus 100 centimeter. So, this is the initial condition. Next, okay. So, continue, and then profile information. So, here it is not able to generate anything. So, this is the pressure head profile, and this is the water content information at one particular time interval, and more information can be obtained if you increase the time and if you run the run the software for different time intervals and you get the data, and you can analyze how the water content changes with the depth. It can be clearly seen, and here if you put realistic values, so the variation in the water content can be very clearly seen. So in that particular case, what we could see is that when soil column and you maintain some certain pressure head, so you can have a porous plate here and connect to a reservoir, water reservoir, you can maintain certain head, could be a constant head. So then the water flow takes place into the soil in this particular manner. So this is how the waterfront advances within the soil due to head gradient as well as the elevation or the gravity effect. This is how it advances in this particular direction. So the distribution of water with the depth. So for example, this is depth Z in centimeters and the volumetric water content if you plot. So here the initial condition is that theta s here and theta I or theta initial value here everywhere else. So you have, so here it is theta s and this is how it is. Slowly it advances with time and slowly it reaches like this. This is how the profile advances. So the volumetric water content increases in this particular moment. This is at time t1, this is t2 and this is t3 and this is t4. Here t4 is more than t3, more than t2, more than t1. So this is how the volumetric water content increases within the soil with time. Such kind of a profile can be obtained using such free software like Hydrus 1D. So here our discussion on steady state flows and transient flows is complete for our course. So far I have discussed only the water flow or water movement through unsaturated soils under steady state and transient conditions. However, in unsaturated soils there could be vapor flow that can take place because of the thermal gradients or any other humidity variations or density of the air, variation in air density across the soil length, there could be vapor flow that takes place. And similarly, in unsaturated soils the air also can get dissolved in water and this air can diffuse through water. So those two cases also prevail in unsaturated soils and those we did not discuss much in our course. In unsaturated soils the vapor flow can take place. The steady vapor flow for unsaturated soils can be described using Fick's law. So Fick's law for steady vapor flow. So here this is a vapor flux which has units of kg per meter square second. So this is diffusivity which has units of meter square per second, and this is the density of vapor which has units of kg per meter cube. So the expression is qv is equals to minus dv del dou v. So this is meter square per second into kg per meter cube. So the meter square and here dou by dou x comes because from del operator you get dou by dou x. So this is 1 by meter also. So therefore the units are satisfied on both sides. So this particular expression, the rho v, we have earlier seen the density of water which can be written as molar mass of water or moist air times uv vapor pressure divided by RT gas constant and temperature. So the variation in density of vapor is essentially due to change in RH and change in temperatures which can be expressed as MW UV sat times RH you get. So, therefore, divided by RT times change in RH minus MW times RH divided by R times UV sat del T by T square minus del UV sat by capital T. So, this is the expression for del rho V. Once you simplify this and substitute in this expression, so the expression for steady vapor flow as given in Lou-Lycos is QV is equals to minus dV rho V sat times del RH by RH minus del T by T plus lambda MW del T by RT square. So, this expression from Lou-Lycos textbook for steady vapor flux is this. Here the variation of relative humidity and variation of temperature could be considered here. This lambda is latent heat of vaporization of water. So, especially these steady vapor flux conditions are encountered in the nuclear waste repository, which I mentioned in the beginning of the course, that you have a copper canisters. This is a copper canister which contains the nuclear waste. These are all copper canisters which are placed at different spatial distances, and this is compacted back in a pit. This is placed and which is backfilled with the bentonite. So, this is bentonite backfill. These are all bentonite backfills, and so this is an access tunnel below a depth of maybe several thousand meters below the ground surface. You come down by tunneling several tunnels, and you reach this access tunnel, and you make a pit here, and the disposal pit you place the canister and then backfill it with bentonite. This is called buffer, bentonite buffer. So, generally buffer material contains bentonite alone, and then which is compacted at very high densities, and then once this is compacted and these access tunnels are filled with backfill material, again bentonite plus other materials also kept, and this is buried. So, now once this is placed, this canister is hot at higher elevated temperatures because of the radioactive elements, and the temperatures are expected to be around 60 to 80 degrees or even more than that sometimes. And the surrounding rock mass, this whole thing is a rock mass, so which is saturated generally at that level. This is completely saturated. So, the water movement takes place into the bentonite buffer material, and this bentonite is initially at air dried state. So, this is unsaturated condition. Heat conduction takes place in the opposite direction, and water movement takes place in this direction. Generally, the coupled phenomenon need to be solved because there is a vapor flow, there is a heat conduction taking place, there is a water flow that is taking place, and it exerts some pressure around the surroundings. The bentonite exerts pressure around the surroundings, that is a mechanical pressure that is exerted. So, hydro, thermo, mechanical studies are often conducted by coupling all these analyses together. So, in this particular cases this is very important. However, as this course is for preliminary audience, so these advanced issues are not discussed in this particular course. Similarly, often we see that the air gets dissolved in water when you apply very high pressures, etc. This dissolution takes place, that we have discussed in the beginning of the course. So, when the dissolution takes place, this air which is dissolved in water also travels from higher pressure to lower pressure. So, that is a diffusion that takes place within the water. So, that is expressed by again Fick's law. The steady air diffusion equation becomes a QA, that is a air flux, is equals to minus d diffusivity times delta C. So, QA is air flux which has units of mole per meter square second, and the diffusivity has units of meter square per second, and this is air concentration which is expressed in mole per meter cube. So, this is the steady air diffusion equation. Now, this equation has many applications, especially we discussed the axis translation technique earlier. In the axis translation technique, you have higher entry porous disc which separates the water reservoir So, this is the water reservoir. So, here water pressure can be applied and your soil sample will be here, and this is porous disc. So, you have air chamber. So, here you apply a required air pressure. So, here there is a air pressure that is maintained, here water pressure is maintained. Generally this air pressure is very high, as high as higher than the atmospheric pressure. So, here due to the water pressure that is exerted, you maintain a UA minus UW pressure, that is suction that is controlled within the chamber, because water pressure is UW and this is air pressure. Generally this water pressure is equal to the atmospheric pressure, that is 0 if you consider it to be gauge pressure. So, then in this particular case, if you have dissolved air in the water, so this is air pockets, some air pockets are here available. So, generally this happens when you do not flush the higher entry disc very often, and then some air pockets may be left over and those will be available on the water side and sticking onto the higher entry porous disc, and as shown here. So, now when you are conducting a test at equilibrium, you have a air pressure that is maintained here and there is a water pressure that is maintained nearly close to 0. So, if there is a pressure difference that happens, then this air pockets would diffuse through this higher entry porous disc. So, this air will diffuse through this higher entry porous disc. So, because there is a pressure difference between two chambers across this higher entry disc, the air diffuses through this porous disc, and because of this pressure gradient, and the diffusion can be estimated using this particular expression if the flow is steady state. If vapor flow or air diffusion is not steady or time dependent, then we need to combine these expressions with mass conservation, and transient equations can be developed, and those transient equations can be utilized for understanding the variation in flux with time. So, in summary, we have so far seen the steady state flows and transient flows through unsaturated soils. In steady state flows, we started off with how the hydraulic head, that is a total head which consists of matrix suction head and osmotic suction head and the elevation head. In case of horizontal flows, this elevation head is negligible or 0. So, then the matrix suction head plus the osmotic suction head, the summation or the combination would influence the flow behavior. In the absence of solute in your soil system, then only the matrix suction head that plays a role. So, then this matrix suction head, how it varies with spatial distribution for steady state flows we have seen. For steady state unsaturated flows, the suction head varies non-linearly with distance, even though if you consider a linear form of hydraulic conductivity function. In case of vertical flows, we require the data of hydraulic conductivity function and soil water characteristic curve for obtaining the spatial distribution of matrix suction head profiles or total head profiles, and we have derived implicit expressions, and we have also seen how to solve these implicit expressions. And coming to the transient flows, then we have discussed the transient flows. In transient flows, we have used simplified expressions given by Green and Amt initially for horizontal flows and vertical flows. Here how the sharp wetting front moves with time was obtained, and this is well corroborated for coarse grained soils because of the assumptions made in this particular analysis. As these are very old approaches, they try to get analytical solutions, and they had many simplifications and they got analytical solutions. And after that we moved beyond this particular analysis, and we have seen that how Terzaghi got influenced in giving the capillary raise height or capillary rate of capillary rise in soils based on this Green and Amt analysis. And beyond that we move to the proper analysis, or considering the mass conservation. We have derived Richards expression, and this Richards expression we have solved using Boltzmann transformation, and the diffusivity variation with respect to volumetric water content can be obtained using this particular form of equations called Clute and Bruce. And the finite difference analysis of mixed form and other forms of Richards equations can be obtained for accurate analysis, and we have demonstrated how the equation can be approximated by taking a theta form, and the software, that is a Hydrus 1D, is demonstrated, and other flows like vapor flow and air diffusion are briefly discussed. Thank you.